Hello, and welcome to this series of lectures on the satisfiability problem for fragments of first-order logic. My name's Pratt-Hartmann, and today I'll be talking about the first-order decision problem. I'll assume basic knowledge of mathematical logic and computational complexity theory, and I'll present the general ideas behind the whole series of lectures which will follow. I won't be going into great technical detail today. If you want to see the technical explanation, then I refer you to chapter 1 of my book Fragments of First-Order Logic, published by Oxford University Press. Let's begin with a problem. Imagine a football league in which every team plays every other, under rules ensuring that each match produces a clear winner. Now define a pretty good team to be a team X such that for any other team Y, either X beats Y or X beats some team which beats Y. Comes as something of a surprise to learn that there is always one pretty good team, at least one. Let's see why this is true. We'll proceed by induction on the number of teams in the league. So here's the league. Let the set of teams be big A. If there's just one team, the statement is trivial, so we can assume there's at least two teams. Okay, so let's pick one of the teams in big A, call that little a, and let B be the remaining teams, so it's a non-empty set. By inductive hypothesis, there must be a pretty good team with respect to big B, call that little b, and let big B prime be the set of teams in big B that little b beats. Must be some set. So little b beats all of the teams in B prime, and the remainder of the teams in big B are beaten by one of the teams in big B prime. Now, either A beats all of the teams in big B prime together with little b, or one of those teams beats A. If the former, then A is a pretty good team with respect to the whole league, because A beats all of the teams in B prime together with B, and all the remaining teams are beaten by one of the teams in B prime, so A is a pretty good team. On the other hand, if one of the teams in B prime together with little b beats A, then little b is a pretty good team with respect to the whole league, because B beats all of the teams in B prime. The remaining teams in B are beaten by some team in B prime, and A is beaten either by a team in big B prime or by little b. So either way, there is always a pretty good team with respect to the whole league. This completes the induction and proves the claim. Now, this is not a matter of football, of course, but of logic, because what the argument in fact shows is that the following first-order formula is true in every finite structure. So here's the formula. It's a conditional. The antecedent of the conditional says that for any x not equal to y, either rxy or ryx. Well, if you read r as beats and think of x and y as teams in a league, then this just says that for any two teams, either one of them beats the other. The consequent of this conditional says that there's a team X such that for every other team Y, either X beats Y or X beats some team which beats Y. In other words, X is a pretty good team. And so this conditional just expresses the situation about the football league that we just talked about. So this formula is true in every finite structure. Of course, this formula isn't true in infinite structures, because suppose we interpret this formula over the natural numbers and we read R as being the relation of is greater than. Then the antecedent of this formula is true because the natural numbers are linearly ordered, but the consequence of the implication is false because there is no greatest number. So this formula is true in every finite structure, but it is not true in every structure. As we might say, it is finitely valid, but it is not generally valid. It's not valid. So a formula is said to be valid if it's true in every structure, and finitely valid if it's true in every finite structure. We've just given an example of a formula which is finitely valid but not valid. It's easy to give an example of a formula which is valid, and therefore, of course, automatically finitely valid, or indeed neither finitely valid nor, or in fact, not finitely valid, not just not valid, I should say. So here's some questions. Does there exist an algorithm to determine whether a formula of first-order logic is valid? Does there exist an algorithm to determine whether it's finitely valid? In other words, can we automate this reasoning that we just went through? So that's the question. Here's the formula which we just showed to be finitely valid but not valid. Can we make this reasoning effective? This problem for first-order logic was most clearly formulated by David Hilbert and Wilhelm Ackermann in their book Grundzüge der theoretischen Logik in 1928. Of course, the problem was generally known at the time, but this is probably the first clear formulation of the problem. And it came to be called the Entscheidungsproblem, or decision problem. And so that's the problem we'll be talking about in these lectures. Now, the Entscheidungsproblem was shown not to admit of an algorithmic solution only about 10 years later, independently by Alan Turing and Alonzo Church in 1936. And their work was clearly inspired by earlier work of Kurt Gödel. Specifically, Turing defined the notion of a Turing machine, as we now call them, effectively a simplified model of computation. So a Turing machine you should think of as a computer program or an algorithm. Essentially, it takes an input and it runs for a certain time, possibly forever, and assuming it stops, then it stops with an answer, yes, we have a positive answer, or no, we have a negative answer. In general, Turing machines can produce any sort of output, but we're interested in the case where they just give an answer to a decision problem, yes or no. Now, Turing identified the notion of an algorithmic solution to a problem with the existence of a Turing machine able to solve it. That is, a Turing machine which gives the right answer and which is guaranteed to stop in every case. So, let's be a little bit more formal about this. We can think of any decision problem as a set of strings, the possible inputs to the problem for which the answer should be yes. So we give an input to the problem, that's a string of symbols, in our case a formula of first-order logic, and the problem we think of as a set of formulas which are valid, the set of formulas for which the answer to the decision problem should be yes. Now, a set of strings, L, is said to be computable or recursive if there's some Turing machine, M, that's guaranteed to halt and that terminates successfully on input X, if and only if X is a member of the set L. So we give M some input, a string X, and this Turing machine is supposed to say terminate. It must always terminate, and if it terminates with the answer yes, if and only if the string X is in L, we think of the Turing machine as deciding the language L, or deciding or solving the problem constituted by L. There are two slightly weaker notions here. A set L is said to be recursively enumerable if there's some Turing machine that terminates successfully on input X if and only if X is in L, but the Turing machine is not required to terminate in all cases. So if the answer is yes, the Turing machine has to be able to terminate and say it successfully and say yes. If the answer is no, then the Turing machine either terminates with the answer no or runs forever. Similarly, a set L is said to be co-recursively enumerable if there is some Turing machine M that terminates successfully on input X if and only if X is not in L. In other words, if L is the complement of a recursively enumerable set. And it is easy to see that a set is recursive if and only if it's both recursively enumerable and co-recursively enumerable. So what Turing effectively did was to show that the set of strings corresponding to valid formulas is not recursive. Okay, that's valid formulas. What about finitely valid formulas? Well, in fact, using an essentially similar argument, Pratt-Hartmann showed in 1950 that the set of finitely valid formulas is also not recursive. Thus, neither the satisfiability problem nor the finite satisfiability problem for first-order logic admits of an algorithmic solution. And the answer to Hilbert and Ackermann's question is simply no. On the other hand, algorithmic solutions of the Entscheidungsproblem were known for various fragments of first-order logic. If you restrict first-order logic to a smaller language, to a subset of its formulas, then we can give an algorithmic solution to the question of whether a given formula is valid or not. For example, it was known from 1915 that the monadic fragment of first-order logic is decidable for validity. That is, the monadic fragment is the set of formulas of first-order logic in which only one place predicates occur. So there are no binary relations, only one place properties. Similarly, all formulas, if you restrict attention to formulas such that all the quantifiers are at the front and all existential quantifiers precede all universal quantifiers, then that fragment too can easily be seen to have a decidable validity problem, and that was shown by Bernays and Schoenfinkel. You can even add a single universal quantifier in between blocks of existential quantifiers. So if you have formulas where all the quantifiers are at the front, you have a block of existential quantifiers, a single universal quantifier, and a block of existential quantifiers, then that fragment too can be shown to be decidable for validity, and that was shown by Wilhelm Ackermann already in 1928. And finally, more impressively, you can have two universal quantifiers here, provided you don't have equality. So if you have consider the fragment of first-order logic consisting of equality-free formulas, where all the quantifiers are at the front, you have a block of existential quantifiers, two universal quantifiers, and another block of existential quantifiers. Deciding validity of formulas in this fragment, again, can be shown to be algorithmically solvable. There's a Turing machine which will answer the question correctly. So, Hilbert and Ackermann's Entscheidungsproblem, decision problem, in fact becomes a classification problem. For which fragments of first-order logic can we decide validity? And that classification problem is the subject of this series of lectures. Usually, the problem's posed in a dual form. So a formula phi with free variables x bar is said to be satisfiable if for some structure A and some tuple of objects a bar from that structure, that tuple satisfies phi in the structure A in the usual way. So a formula is satisfiable if it can be satisfied. Obvious sense. In the case where phi has no free variables, a satisfiable formula is simply one which is true in some structure. A formula is finitely satisfiable if it's satisfied in some finite structure. So we see that a sentence phi, a sentence, by the way, is a formula with no free variables. A sentence is finitely valid if and only if its negation is not finitely satisfiable. Similarly, a sentence is valid if and only if its negation is not satisfiable. So validity and satisfiability are dual notions. If we have an algorithmic solution to one of these problems, we have an algorithmic solution to the other. So it's just as good, as far as we're concerned, to solve the satisfiability problem. And normally, when we talk about the Entscheidungsproblem or the decision problem for first-order logic, we pose it in the form of a satisfiability problem. Finally, we apply the terms satisfiable and finitely satisfiable to sets of formulas with the obvious meaning. So a set of formulas, big phi, is satisfiable if there is a structure and a tuple of elements to be substituted for its free variables, which make all of the formulas in that set true. Okay, so that's satisfiability and finite satisfiability. So, if L is any fragment of first-order logic, that is, a set of formulas of first-order logic, not necessarily the whole of first-order logic, the satisfiability problem for L is the following problem. Given a finite set, big phi, of formulas of that fragment, return yes if phi is satisfiable, no otherwise. The finite satisfiability problem is the corresponding problem regarding finite satisfiability. You're given a finite set of formulas, return yes if it's finitely satisfiable, no otherwise. Now, most fragments of interest are closed under conjunction, or effectively closed under conjunction. And in that case, we may take the inputs of the satisfiability problem not to be a finite set of formulas, but a single formula, and usually that will be the case. So we ask, for which fragments L of first-order logic are the satisfiability problem and the finite satisfiability problem for L decidable? Of which fragments are these recursive sets? Now, the principal fragments of first-order logic, which are known to be decidable for satisfiability and finite satisfiability, fall, as it happens, into four major classes. We have the two-variable fragments, guarded fragments, quantifier prefix fragments, and the variable ordering fragments. And I'll be talking about these fragments in later lectures in the series. All of these fragments include what's probably the most venerable logical system of all, the Aristotelian syllogistic. And in fact, the Aristotelian syllogistic is, of course, also therefore decidable for satisfiability. So, in this series of lectures, I'll be explaining the main ideas behind the decision procedures for representative fragments in these classes. And I'll be starting in the first of these technical lectures with an analysis of the Aristotelian syllogistic. Now, it might be helpful at this point to mention one or two more, slightly more technical details. A fragment of first-order logic is said to have the finite model property if all satisfiable finite sets of formulas in that fragment are also finitely satisfiable. Equivalently, if the satisfiability problem and finite satisfiability problems are the same. Clearly, finite satisfiability entails satisfiability, but not conversely. If they do coincide for a particular fragment, we say that the fragment has the finite model property. Now, there's a close relationship between having the finite model property and being decidable for satisfiability. So I should explain that. In 1930, Kurt Gödel showed that the set of valid sentences of first-order logic can be axiomatically characterized in terms of a finite list of axiom schemas and inference rules. So the idea is that Gödel could give a finite list of axioms, or axiom schemas to be perfectly precise, a pair of inference rules, in fact generalization and modus ponens, but they're just rules for turning one bunch of formulas into another. And all of the valid formulas could be derived from these inference rules. So if a formula is valid, first-order logic, there's a proof that it's valid using Gödel's axiom schemata and inference rules. It follows that every fragment of first-order logic with the finite model property has decidable satisfiability problem. To see this, suppose we're given suppose we are working in a formula with the finite model property, and you give me a formula phi in that fragment. I can take Gödel's axiomatic system and start proving theorems. In fact, I can keep proving theorems on and on and on until all possible, in a way which proves all conceivable theorems. So this is an infinite process, of course, but for every valid formula, there will eventually come a time when the proof of that formula is given, because all proofs will be enumerated. In parallel, I can construct all finite models one by one and simply check whether they are models of phi, or finite structures. And I can create all finite structures, enumerate them, and check for each of them whether it is a model of phi. So as long as the fragment has the finite model property, eventually either I will obtain a model of phi, or I will obtain a proof that the conjunction of formulas of phi is not true. A proof of the validity of this formula here, the negation of the conjunction of the formulas of phi. Big phi is, of course, just a finite collection of formulas. So if a fragment has the finite model property, then it is decidable for satisfiability. And of course, by definition, the satisfiability and finite satisfiability problems coincide. I should add that the converse is not true. It's well known that there are fragments which are decidable both for satisfiability and finite satisfiability, but which do not have the finite model property, and we'll be encountering some of those later on in the series. If a problem is algorithmically solvable, as it will be in the case of the satisfiability problem for certain fragments, the obvious question is, how quickly? And we'll be giving complexity analyses of the various fragments that we consider, and in doing so, we'll make use of the familiar hierarchy of complexity classes: n-log space, p-time, np-time, p-space, exp-time, nexp-time. I shan't be defining the classes in these lectures. I shall assume that you have access to text on computational complexity theory, but very roughly, n-log space is the collection of languages that can be recognised by a non-deterministic Turing machine using only logarithmic working memory. P-time, the collection of languages that can be recognised by a Turing machine using in polynomial time. NP-time, the language is recognised by a non-deterministic Turing machine running in polynomial time, and similarly for the larger classes, p-space, exp-time, nexp-time, and so on. So in particular, if the satisfiability or finite satisfiability problem for some fragment of first-order logic is decidable, we want to know what complexity class these problems lie in. Now, saying that a problem lies in a particular complexity class gives an upper bound on its complexity, not a lower bound. To give a lower bound, we use the concept of reductions and hardness. So if curly C is a complexity class, a problem is said to be C hard if any other problem, Q in C, can be reduced to it using so-called menu on log space reduction. I won't explain that in these lectures. Again, I refer you to a text on computational complexity theory. And the problem is said to be C complete if it is in C and C hard. So for a given fragment of first-order logic, we want to know is its satisfiability problem and its finite satisfiability problem decidable? If so, what complexity classes do they lie in? And if we can we determine for what complexity classes they are complete. What we observe, unsurprisingly really, is a trade-off between expressive power and the complexity of decidability. The complexity of satisfiability, indeed the decidability of satisfiability. So the satisfiability problem for the Aristotelian syllogistic, a very simple logic, inexpressive logic, is n-log space complete, low complexity. The satisfiability problem for all of the decidable quantifier prefix fragments that I mentioned the Bernard-Schoenfinkel fragment, the Ackermann fragment, the Gödel fragment. All of these are nx time complete. So higher complexity, still decidable, nx time complete satisfiability problems. There is a further fragment which I haven't mentioned yet called the fluted fragment. This is one of the so-called variable ordering fragments which I mentioned just in passing. And this fragment, which I'll be talking about in a later lecture, is decidable, but the complexity is higher than any class in the standard hierarchy of complexity classes that I had on the previous slide. So it is a so-called tower complete problem, so very, very high complexity indeed. And eventually, of course, we reach our decidability. If the finite satisfiability problem is for the whole of first-order logic is undecidable. In fact, it is recursively enumerable complete, and the satisfiability problem is co-recursively enumerable complete. Remember, I gave definitions of those notions just a moment ago, and in fact, of course, remembering that a problem is decidable just in case it's both recursively enumerable and co-recursively enumerable, well, you can see that the finite satisfiability problem for first-order logic is recursively enumerable but not co-recursively enumerable, and the satisfiability problem is co-recursively enumerable but not recursively enumerable, and so those problems are both undecidable. What you'll need for these lectures. I shall assume that you understand basic first-order logic, formulas, structures, satisfaction by tuples of elements, usual basic first-order logics of Chapter 1, Chapter 2 of standard textbook. I'll assume that you understand the basics of computability theory, what a Turing machine is, what a recursive function is, what recursively enumerable and co-recursively enumerable sets are, and how to think about these things generally. I'll assume you understand basic complexity theory, deterministic and non-deterministic Turing machines, alternating Turing machines, standard time and complexity bounds, reductions, hardness, and completeness. A brief overview of the technical details can be found in my book, Fragments of First-Order Logic. If you look in the first chapter, there's a summary of all the required technical notions, and of course there are plenty of textbooks on this subject, references to which you'll find there.